Thank you very much, and good afternoon from my behalf, and thank you for inviting me here. And I'm gonna tell you about the direct air capture and its energy requirements in future scenarios. So I will first go through a little bit for the need for direct air capture. What is its role in our pathway towards net zero greenhouse gas emissions? I will talk about DAC key features, and then about the projections of DAC's energy consumption in these net zero scenarios, and then finally some conclusions. So here you can see a simplified illustration of an IPCC climate change mitigation scenario towards 1.5 degrees climate targets. So the warming, to stop the warming to 1.5 degrees. And as we all know, that would require very rapid and drastic emission cuts starting from now to reach the net zero emissions around 2050. But just reducing emissions is not enough. We need to, in addition to that, we need to increase the carbon sink in the land use and forestry sector. And even in addition to that, we will need to remove carbon dioxide from the atmosphere to keep the temperature rise lower than 1.5 or even 2 degrees. And this is because the later we start the very drastic emission cuts, the more we will need of this carbon dioxide removal. So of course, it's best to really focus on cutting our emissions to reduce the dependency on these removals later on in the century. And when we talk about direct air capture, it can have a role in both sides of this equation. It can help to reduce the emissions, as we heard earlier already, some applications, and then it can also provide us with carbon dioxide removals. So direct air capture of CO2 literally means capturing CO2 from the atmosphere, from the ambient air. And then with that CO2, we could do CCU, as said in the PS presentation. We could use hydrogen and CO2 to produce different kind of products. So e-fuels, also polymers, chemicals, and components, for example, in construction materials. So here we can gain emission savings and emission reductions if we replace products with higher emission intensities. Then the other option, as said, is to store the CO2 permanently. So this would be in the geological storages or by mineralizing the CO2, so that the storage would really be permanent, lasting for thousands of years. And this carbon dioxide removal, of course, there we also need to understand the life cycle emissions of the process. So the emissions of this capture and storage process need to be lower than the amount of CO2 captured. So DACs could be used for both of these processes. And here we have very high energy demand for the DAC process itself, and also for the electricity production for hydrogen. And for the DAC process, the energy demand is very high because, of course, in the ambient air, we have very low concentrations of CO2, so we need a lot of energy to capture that. We have two main types of DAC technology, so solid DAC and liquid DAC. And in the solid DAC, we have a solid absorbent, which is regenerated then in low temperatures. This technology is suitable for modular installations, so it could have small-scale solutions or then larger-scale plants with several modules installed. And as we have low temperature, here we could benefit from waste heat, or this technology could possibly be also combined with these small nuclear reactors. Then we have liquid DAC, where we have, for the chemical capturing process, we have liquid sorbent, and it's regenerated in very high temperatures. So here the temperature required is around 900 Celsius degrees. And this is a technology suitable for large-scale installations. And currently, this is based on an IEA estimate. The cost for this liquid duct is lower than for solid duct, but the cost of both technologies is still quite high. So you can see here the price would be from 3 to 550 US dollars per ton of CO2 captured. And this could be compared, for example, the price of the current emission trading system, where the price of ton of CO2 is around 80 to 100 euros. But we will see how the price of these technologies will then develop in future. There are also recent studies which say that especially this solid duct, the energy demand is dependent on the location of the plants. So actually in the northern conditions where we have colder and more humid air, the energy consumption could be lower than in very hot surroundings. So with the blue color, the energy requirement is lower, and with red colors it's higher. So this could be a suitable option for the northern countries. What we have done at VTT and in this NEGEN project that has just finished, we have modeled our own mitigation scenarios. So these are also these 1.5 degree scenarios where we try to illustrate the potential need for these technologies removing carbon dioxide from the atmosphere. And this is a modeling made by cost optimization models, so it shouldn't be taken as a forecast of the future, but it can give us a scale of the solutions needed. So on the upper figure here, you can see how the emissions should be cut down. We have 3 different scenarios, one focusing on technological development, the second one focusing on environmental constraints, and the third one focusing on security. And here we have applied all kinds of all the different technologies known for the carbon dioxide removal. So mainly DACs and BECCS are these large-scale technologies, but then we have also other solutions. And we can see that as in the IPCC scenarios I showed in the beginning, the demand for carbon dioxide removals could be in the tens of gigatons in the second half of the century globally. And in the second scenario, so in the middle figure here, we strictly limited the biomass availability due to some sustainability concerns. And there you can see that the role of ducts, so the pink column, it becomes even more important than in the scenarios. And on the lower picture, we have the electricity demand in these scenarios. So if So for these emission reductions, we of course need electricity for many things. We need to electrify our transport sector, we need to electrify our industries, we need the hydrogen economy and the CCU products. And in addition to that, we would need the electricity or the energy for ducts production. And in these scenarios, the consumption for ducts could be even from 5 to 11% of the total global electricity demand around year 2070, when the use of this technology peaked. So this can be a very important issue to think about in the future planning of our energy systems. So where we are at now, this is from the State of CDR report. So they have tracked the current projects for carbon dioxide removals. At the moment, they concluded that we are globally doing around 2 gigatons per year of carbon dioxide removal, but that's mainly done on this with this conventional CDR, so afforestation, reforestation processes, and carbon farming. And only a tiny bit is done with these novel methods, so technological methods such as BECCS that was mentioned earlier, or biochar production. And actually DACS is their last little tiny black line. DACS is inside that. So basically we only have some demonstration plants existing. So there is a huge development that should be done with that technology. But in the near-term plans, the DAX projects are increasing starting from the 2030s. So to conclude, direct air capture can be used for climate change mitigation in two ways, providing CO2 for CCU products and then creating emission reductions, or if the CO2 is stored permanently, then DAX could create carbon dioxide removals from the atmosphere. And low emission electricity or heat will be needed for these technologies, and this can be very significant towards 2050s and beyond. And we will need more regional studies on how DAX systems could be combined with the local energy systems, and which would be the most beneficial to use this technology. And at VTT, we are currently trying to do more specific modeling for Finland and to see if DAX would be interesting option here. And I know also that my colleagues are studying the possibility to combine DAX with SMR reactors. And there's actually something that could be done during those low demand months during the summer. But then it's a question about the cost. And of course, VTT is also working on many CCUS projects doing the technology development. So thank you very much. And if you're interested on carbon dioxide removals, please visit our NEGEM website to learn more.
And again, do we have any questions, comments, queries, anything you would like to know more about? Okay, please.
Thanks a lot again, Professor. You're very creative. I have one question. Are there similar projects worldwide, not only Europe?
Similar projects like
on the same topic.
On the technology.
The technology, similar technology.
Yeah, well, US is very active on DAX. They have invested a lot in their DAX program, so they are moving faster than Europe, I think, at this moment.
Thanks a lot.
You should just set some position. Because in past I was involved in serious accident of nuclear power plants. Do you have any analysis what would happen in case of permanent storage of CO2 if due to some accidental conditions this CO2 will release outside?
Yeah, well, of course, it would be very bad if it would release in high concentrations. It would kill the people. but what is talked about here is the geological storage under seas mostly. So the projects that are going on in Norway, for example, have stored CO2 for a long time. So this is kind of proven concept, but of course, in this scale, it's not proven, and we don't know if it will work out. So it's really something where we need to focus also to understand what is the potential for this.
Maybe the second question. Okay, it's in such a location, what would be the capacity concerning the volume and concerning the duration for the healing of such?
Well, I must say I'm not an expert on these storage systems, but I have understood that it's case specific, and normally the storage potential is not considered as a very big restrictions in these modeling studies, for example. So we believe that we have potential for this geological storage. Of course, it hasn't realized yet, so we don't really know. And there have been some surprises in these projects in Norway. So, for example, the CO2 didn't stay in the layer. They were thinking it would stay, but it stopped somewhere else. So probably all of this potential that we think is there won't be available at the end. So we also need to think which CO2 we need to store there.
There is also a question on the internet on if there's any information on the flexibility of the DAX processes. So can they shut down and ramp up, or are they continuous?
Unfortunately, I'm not a technical expert in that level, but we have Cyril online, maybe he can respond. I know this. So there are better experts on the detailed questions that we did.
Cyril, if you're online, please answer. I've enabled your microphone.
Yes, hello, good afternoon. Cyril here. The question is, how flexible are DAC application in terms of energy demand? If you want to make DAC systems flexible, you would need a thermal storage system for that, in the sense that when you start heating up solid sorbents, the heating has to continue until you reach the desired temperature. We have experienced previously that when you make it dynamic, you have actually a lot of losses to the system. The next question, can the process run efficiently according to weather patterns? Both yes and no. If the main purpose is to capture CO2, the sorbents used in this solid DAC loves cold weather, but no, in the sense that if there's a lot of humidity, water becomes a parasitic loss to the production of carbon dioxide. Thank you.
It's good to have the experts in the house. Yeah.
Okay,
Thank
so
you.
if